Okay, take two. I had a little listen to that. I really have no idea what was happening with the mic there. I know I unplugged the microphone yesterday, so I had to plug my phone in. And then I replugged it in and it was fine during my Zoom sessions earlier. Um so I'm just sort of hold on, let me just pop something in the streaming updates in Discord to let people know I have rejoined. Okay. So what I'm going to do is I'm going to wait for people to join and see if the mic issues have been fixed. Hello, Vivan. Can you tell me how my microphone is sounding? Because I was just live for a little bit. Sounds fine now. Great. Perfect. No idea what that issue was. Okay. Apologies. You get take two. There's no welcome. There is no hello. Tech has denied us the good things in life. All right. So sounds great. Let me jump back straight back into it. So what we were discussing, we just started off, it was like right at the start of stream. We were discussing density, specifically combining densities for different objects. And we got to the point where we combined, said that the total density was the total mass divided by the total volume. And then that the individual masses were their respective densities times their volumes. And then we got to this point where it was the sort of volume fraction of A times the density of A, and the volume fraction of B times the density of B. Now, the point that I was just about to make here is that for any of you doing chemistry, this is very similar to how you find the average atomic mass. So, for instance, if something is 25% chlorine 35 and 75% chlorine 37, then you kind of take the average in the same way. So out of the volume of 100, 25 would be 35 and 75 would be 37. So it's that same kind of idea. So you can use that sort of interdisciplinary understanding to help you with these combining densities. Now, hold on. This keyboard I can put away. So that's how to find, for instance, the density of alloys. So for instance, let's take some specific example. Let's say we had... Oh, yes, as always, by the way, always drop things in the chat. That'll help me sort of direct this to where you guys need it. Someone says, there were difficult materials extended response questions, 4 to 6 markers I saw from some AQA old spec papers, where you have to relate material properties such as Young modulus and stiffness, etc., to justify which materials would be appropriate for different scenarios. Ah, that's great. I'm going to hold on to that in the chat. Because when we get to the proper like materials Young modulus side of things, we'll definitely get into that. If you think it should be like appropriate at this moment, like pop it in the chat and I'll like respond. In the meantime, though, let me do the kind of example of this. So let's say we had, for instance, using an example from a textbook, let's say we had a volume of copper as being 3.3 times 10 to the minus 5. And we have a volume of zinc as being 1.7 times 10 to the minus 5. And we have a density of copper as being 8,900. And we have a density of zinc as being 7,100. From this, we can clearly just sort of work out the mass of copper as the density times the volume. Do I have my good calculator in the other room? That is such a shame. I should always learn to have my good calculator equipped with me at all times. Oh well, I'll have to use... In fact, do I hate all these calculators so much I'm willing to open the emulator of the good calculator? Yes, I do believe that is the case. Guys, I'm telling you, the old school class whiz is absolutely the way to go. So it was 3.3 times 10 to the minus 5 times 8,900. Do you do further math? Yes, I do, but is my confidence good enough to stream it? Not necessarily. 0.929. Mainly because it's the one I get asked about the least, because usually people doing further math are like solid enough that they're kind of doing it on their own. So for instance, discrete. Loads of students have done discrete, but I have never been asked about discrete, and so I never bothered learning it. And so it's just a case of like, the better you guys are at something, the worse I am, because I never have to teach it to you guys. Thank you for that. That just sort of helps. So the mass of zinc is 0.1207. The unit's actually kilograms, sir. This is physics. Mind your units. But yeah, so you get your masses. And therefore, the combined mass, the sort of density of the overall alloy. Yeah, there you go. The density of the alloy would be 2937 plus the 0.1207 all over the total volume. So 3.7. In fact, if you guys want to jump ahead of me and actually run this in your calculators, I'm very happy. Like, this is just a simple calculation, so I'm happy to just sort of, you guys can give me spoilers on this one. But in the meantime, let me try and work that out on my own. So 0.2937, 0.1207, 3.3. I'll take your word for that. Is going to be 8288 kilograms per cubic meter. Now, can we think about why this would make sense? It makes sense because we can see that there is more of the copper than there is of the zinc, so it would be weighted towards the copper side of things. So the pure 50-50 average of these two would be 8,000, but I would expect it to lean closer to the copper, so I expect it to be over 8,000, and so that tracks. So that's density. Density, not too bad. Let's talk about springs, especially combining springs. I think I may have spoken about this in another stream, but let's start with the basics first. So the one thing we know about springs, they obey Hooke's law. You know, for Hooke's law, it says that the extension is proportional to the force up to a limit of proportionality. So the force needed to stretch a spring is directly proportional to the extension of the spring from its natural length. In other words, Hooke's law is just F equals kx. To measure the extension, you obviously measure the unstretched length and then the stretched length, and then take the difference. But this also is up to an elastic limit. So we know, and I will be coming back to a lot of these graphs, but the force extension graph should be a straight line up to some limit of proportionality. And we're going to pause there and just talk about the elastic region for now, and then add the rest on. I'll remind you guys how to derive the behavior of springs in series and in parallel. So in series, let's say we have one spring. We know the force on that spring is going to be times k times x for that spring. Now, if we combine two of those identical springs in series, they are identical springs, so the spring constant is the same. So if we apply this force F, if we apply the same force F will equal kx on this spring, which means the extension on this spring will be equal to F over k. And similarly, the extension on this spring will also be F over k. So the total extension will be the sum of the individual extensions, and it would become 2F over k. And if we rearrange this for F, we would get that F is equal to a half kxt. So in other words, this is the equivalent of a single spring of stiffness constant, of spring constant, a half k. So in other words, when we add two springs in series, the effective spring constant is halved. So in a way, it's almost like adding resistors in parallel, where adding these two in series makes the overall stiffness reduced. If we consider instead what happens when we add the two springs in parallel and apply a force, we know that here F is equal to kx. Well, not F. Let's say, let's call this something different. So that's going to be F. I'm going to call these T for tension. So I'm going to say the tension is K times X1 in this guy. The tension is K times X1 in this guy because the extensions have to be the same if they are in parallel. And what we know is that F is equal to 2T. Assuming these are the same spring and have the same spring constant, then the forces will be the same. So it would be 2kx, and therefore the equivalent spring constant here would be 2k. In other words, it's got stiffer, and adding the springs in parallel means that you've added their spring constants. Strictly speaking, you could do this for non-identical springs as well. But I'm going to hold off on that, and I can come back to it if I need to, because I think that might be beyond the scope of the syllabus. No, it's not beyond the scope of the syllabus. In fact, let me do that right now. So this is the case where the two springs are equal, and it kind of gives you a sense of the behavior here, that adding springs in parallel is like adding resistors in series, and adding springs in series is like adding resistors in parallel. We can take this one step further and generalize. So let's say these are now different springs with different spring constants. If I apply force F here is going to be equal to K1x1, and F here is going to be equal to K2x2, where we know the total extension will again be x1 plus x2, which will be equal to F over K1 plus F over K2. And so that's going to be F into 1 over K1 plus 1 over K2. And if we rearrange this for F is going to be equal to 1 over K1 plus 1 over K2 to the minus 1 times the X total. So in other words, this expression here becomes the new spring constant. So in other words, 1 over K is equal to 1 over K1 plus 1 over K2, which is exactly like adding the resistors in parallel. And generalizing for the springs in parallel, if we have these as different spring constants, then again, T1 is going to be equal to K1 times X, and T2 is going to be equal to K2 times X, where they have to have the same extension because they are in parallel. Then the total force becomes the sum of those individual tensions. So it's K1 plus K2X. So in other words, K is equal to K1 plus K2, the equivalent spring constant. We can also think of the meaning of what the spring constant means, right? So if you increase the spring constant, we can conclude two things. The first thing we can conclude is that it requires more force to extend the spring by the same amount. So for a constant extension, you require more force. But also for a constant force, a larger spring constant means you get less extension. So that's two ways of conceptualizing it. One for constant force, one for constant extension. We can also talk about the energy stored in a spring. Because we know for a spring within its limit, elastic limit, that those are proportional, we know that the work done will be F times its delta X. So you can almost think of this as like an integration from first principles, and you will find that the work done to extend the spring equals the area under the curve. Thank you very much. I genuinely don't know where the hello came from. It just sort of sprung out, and I was like, all right, I guess we'll keep that. Although I will say, actually, hold on, comment section. Okay. So like I remember because I was going through and like sort of updating some of like this, you know, the timestamps, and I was going through to kind of get a sense of like, I wonder what I'm like to listen to. And to hear me say it like 10 times in a row from the early days, I was like, God, that's grating, which is why I've tried to like take it down. So it's less like clown carnival levels of energy. Now I'm like, hello, 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 and just sort of nice and calm. That's it. That's it. If you ever want to like get really annoyed by it, trust me, just like watch one video after the other. That's why I brought the energy down. But yes, I'm happy to keep it. I know, right? Saturday stream is bold. Normally I would take Fridays and Saturdays off, but it is exam season and my schedule is like crazy. So yeah, I always open out the Fridays and Saturdays. Oh. So yes, the work done to extend the spring is the area under the curve. This is simply going to be a triangle, so it's going to be a half times base times height. But because f is equal to kx, you get a half kx squared. Okay. So that is the energy to extend a spring. And because this is within the elastic limit, when you take that force off, you will get back to its original shape. So that is the elastic potential energy stored by changing the shape that you can get back by removing that loading force. So now we've discovered that's the nice basic behavior. That is a simple spring undergoing Hooke's law before the elastic limit. Life is not so simple. So now we've got to talk about all the different ways that materials behave in real life when we apply these forces to them. Now I'm about to do the loading and unloading curves. It's work done and energy interchangeable. Yes, given that the definition of work done is energy transferred. So the work done is that's the energy required to be put into it in order to extend it, and it's also the energy you get back when it retains its original shape. There's a subtle difference in that work done is energy transferred, so you always have to keep in your head what it's going from and what it's going to, but other than that, they are pretty interchangeable. Okay, so am I gonna... How best to go through this? So I've got the, do I want to go into stress or strain, or should I do it in terms of force and extension? Let's do force extension. I'll come back to the stress, stress strain. But I want to do, for instance, the rubber band hysteresis loop, which people hate. So as long as we're still on the force extension, let's keep here. So that early one is what happens for a nice spring undergoing Hooke's law, but we can also now consider this hysteresis loop. So the loading and unloading curve looks very, very different. So it loads above with this weird S shape. Now, I used to be able to talk in very, very explicit detail about this, and I think I have since lost the ability, but it's in terms of like, so this is a rubber band. Now, the loading curve goes above the unloading curve. So the way to think about this is that this is the... So if you know from chemistry, rubber is a polymer, and a polymer is a long chain of sort of carbon, has these chemical bonds. These are all sort of like looped together into this like ball. When you apply a force, you have to change the shape of the polymer chains, which requires some bending, twisting, changing of those chemical bonds in a sense. That requires some energy. So what we find is that you've changed it. Even though it's come back to its original shape, the chemical bonds have still gone through some sort of journey to get there, and that has required some energy to go from start to finish. So in other words, if we consider two areas, if this is area A and this is area B, then A plus B equals the work done to extend. And then B is the work done in, is the EP released, I'll say. When it comes back to its original shape. Or the energy released in unloading, right? And what we find is you have to put more energy in to extend it than you get back out again when it comes to its original shape, which means that area A is the internal energy increase of the rubber band because it retains some of that energy as heat. It heats up. So that's the internal energy increase of the rubber band. So some of the energy stored in the rubber band becomes the internal energy of the molecules when the rubber band unstretches, is how it says there. How would you find the areas? Honestly, you would have to do that really annoying thing where you just count the squares. That's not an analytical thing that you can integrate. You would have to just legit count the squares. I know. It's my least favorite part of A-level physics doing that. Now let's discuss some other force extension behaviors. So we said that Hooke's law is obeyed up to a constant of proportionality, up to an elastic limit. After that, it starts to slip. It starts to undergo plastic flow. So the point at which, nope, can't spell. The point at which it stops undergoing Hooke's law is called the elastic limit. Then it undergoes plastic flow. And then when you unload it, it tracks back the original loading curve in parallel. And it does not come back to its original shape. This is now a permanent extension. It would really help if I was one of those people with really pretty handwriting, but I am just not. So you get a permanent extension when you unload it. So that is the case of an overloaded spring, for instance. We've already spoken about the rubber band, which was above. And polythene does some more like nonsense. So this is a metal wire or a spring. And the third case you need to understand in terms of these force extension graphs is polythene, which is, well, it behaves like rubber going up and it behaves like a wire going back down because reasons, I suppose. So it does not retain its initial length. The area between the loading and unloading curves represents the work done to deform the material permanently. Yeah, you're right. It is fairly chemistry. Well, that's one of the reasons, it's one of the reasons I quite liked material science, which is why I chose to do it as a degree. It is that balance between the physics and the chemistry. And you're right that when you're doing polymers, like you do get into sort of chemistry bond things, you get some inorganic chemistry happening. And so you're not wrong about that. And for anyone who doesn't really know what material science is, like I went to Cambridge to do the broad-based sciences degree because I knew I was like a jack of all trades, master of none. But then material science was kind of that perfect interdisciplinary blend that was very practical and not very theoretical, which is why I ended up gravitating towards it. But I could see if you don't like chemistry and you do like theoretical physics, then you would hate this. So apologies for that. Yeah, I gotcha. It's okay. So that is the polythene. This is the one that's sort of least discussed. Electrolysis is great fun. Also, you get Gibbs free energy curves in material science. That's also great fun. Right, let me see if there's anything else here that I need to talk about. So we've done Hooke's law. All right, we need to go back and do stress and strain, and then Young's modulus. Elastic strain energy we've talked about. It's the area under the curve. Oh, wait, no, there is something I haven't discussed yet. There is absolutely something I haven't discussed yet. But I'd rather do it after we do stress strain. So, okay, it's stress strain time. What is stress? What is strain? It's what you're all experiencing right now in exam season. Yeah, ooh, that was an original and inventive joke. So, stress is denoted sigma, and that is the force per unit area. And strain is denoted epsilon, and that is the extension over the original length. And then you get Young's modulus, which is a materials constant. E is stress over strain. By the way, we can combine these equations and say that that is force over area divided by epsilon, so times L over x. So in other words, it's FL over AX. And this is a material constant in the same way that specific heat capacity is, thermal heat expansion, resistivity, these things that are constant for any material. So if you know it's copper, you know the Young's modulus. It does not change depending on the shape or anything else. What the stress and the strain do is they account for the shape changes. So if we have the same material and one of them looks like this and the other one looks like this, yo, what's this? This is material science for A level and IB physics. Although I don't know if it's in the IB syllabus, actually. So if we apply the same force to both of these, sorry, I've kind of blocked this off now. If we apply the same force to these, it's clear that the one on the right is going to extend a lot more, just from your common sense. Because here there's almost less pressure on that, and it's got less to sort of extend. Whereas this, like that force is like really doing a lot, and it's going to extend it quite far. Even though they're the same material, because of the nature of the stress and the strain. So because here, this area is bigger, that means the stress has decreased. And because the length is lower, the extension is lower. Is that? That's probably not the best way of explaining it, but the yeah. That is actually a way of doing this. Because the stress has gone down, and the Young's modulus is a constant, so we can rearrange this and say sigma is equal to the Young's modulus times epsilon times the strain. So if the stress goes down, then the strain goes down. And if length has gone down and the strain has gone down, then the extension definitely has gone down. So that's why this one extends less. So I'm trying to sort of show you how to sort of use the common sense to sort of feed all these ideas through each other to get a real world understanding of what stress and strain means. So you increase the stress by increasing the force or decreasing the cross-sectional area, and you increase the strain by increasing the extension or decreasing the length for a given extension. So it's all about a percentage increase in length, basically. So also, using stress and strain is a very good way of sort of standardizing it for a bunch of different shapes, right? So it doesn't matter if you have a thick spring versus a thin spring, all of those things. So you see in real life, these forces would change the extensions. In fact, for these two, the stress-strain curve would look exactly the same. So oftentimes, instead of looking at an F times X graph, we will look at a stress-strain graph, because that's much more standardized across a bunch of different shapes and practical forms. Does AQA tend to give strain in percent, or is that an OCR thing? I think that's an OCR thing. Let me just check real quick. Because I've got the AQA book literally right in front of me. Where have they defined? Yeah, it's given as no unit. I don't think they give it as percent. Someone asked, just quickly, the chemistry syllabus for IGCSE at Excel is split into part 1 and part 2. Is part 1 for paper 1? Yes. So paper 1 is all of the stuff that shows up. So in fact, I'll answer this real quick. So for the IGCSE chemistry, paper 1 is the stuff that is just on like the part 1, and paper 2 is just the sort of advanced chemistry for chemistry only. So the idea is that if you are doing edXL double award, you will just sit paper 1 in the biology and the chemistry and the physics. So any of the chemistry only stuff will only show up in paper 2. Okay. Loving the chat's very active today, and I like that. Okay, so we've introduced this idea of stress and strain. Oh, okay. Following on from that, is paper 2 only part 2? No. Part 1 stuff can show up in part 2 because you are expected to still understand it. It's just that if you have part 2 stuff, if you have part 2 stuff, that it will only show up in paper 2, but it doesn't mean that paper 1 stuff can't also show up. Cool. So here, let's talk about what these stress strain things do for different materials. So stress strain curves, first of all, we know it obeys Hooke's law. So instead, I'll call this stress strain. We know it obeys Hooke's law up to the elastic limit. And then what it's going to do is it's going to curve down where this is the yield strength. Sorry, I've probably not given myself enough runway here. Let me try this again. Have you done anything on particles? No, sorry, on practicals, like how to approach them using common sense, not just purely memorizing them. I'm pretty sure I did do hold on a minute, did I? I have a memory of doing practical physics, so combining the different uncertainties, using and how to turn your models, your equations from the formula sheet into a straight line that you can plot and interpret the gradient and intercept. I'm pretty sure I've done that. So you can have a look at that and correct me if I'm wrong. I'm happy to be corrected on that. That's very paper 3 stuff. Someone says, to what extent can I answer the sentence-based 3-4 markers with mathematical symbols and proportionalities rather than long sentences? I think you can actually. I think physics, you can get away with bullet pointing even. The only exception to that is I know some syllabuses, sometimes they'll explicitly say the quality of your written communication will be assessed, in which case you have to write in good, clean sentences. But I think physics, equations are a very good way of demonstrating the understanding they're looking for. So I'm in favor of that. So here, kind of, in fact, and then what I'll do is I'll just sort of draw straight, and it curves, and it goes insane, and it stops. So so these things are all labeled differently. So this is the yield strength, or the yield point. This is your elastic limit that we saw before. So past the elastic limit, you will get plastic deformation, which is the permanent shape change. And then what happens is it just goes crazy. If you increase the stress a little bit, you get a huge increase in strain, which means it really just starts, it just lets rip. Like it just sort of starts flowing, like sort of like if you imagine stretching bubble gum, like it just goes. And then you get this, which is the ultimate tensile strength, which is the largest stress that can possibly be accommodated by the material. So ultimate tensile stress. And then you get to here, which is your breaking stress. So that's where it eventually snaps. This is, of course, assuming that plastic deformation is possible. So this is very much for a wire. Metals, we know, can undergo plastic flow. The layers of atoms can slide over each other. So you can pass this elastic limit, get the atom starting to flow, and it starts to undergo plastic deformation. And if you keep going, it eventually goes ballistic. Strength and stress are often used interchangeably, yes. So like the strength, is that true? My material scientists, my professors would get me very upset with me for not understanding these as well as I used to. But yes, so if we're talking about the strength of the material, we're usually talking about this ultimate tensile stress. But these words do start to mean something very specific. So for instance, brittle starts to mean something very particular. So we can talk about different types of things. So we can talk about brittle versus ductile, for instance. So ductile, I would describe this as ductile. And depending on this, it could be quite strong. Now, something like glass might be strong but brittle. Why is ultimate tensile stress above the breaking stress? Great question. The reason why great question. You get into it comes into the sort of dimensions of the thing. So is the wire basically what would happen is if the wire starts off roughly cylindrical, what you find is that it kind of, as it extends, there's eventually this bit where it kind of dips in the middle, and then it snaps, and it would kind of snap with like a frayed edge. And I think it's to do with all this sort of shape change stuff, where it's like, in this particular bit, the area has decreased, which means the stress will have gone up, but the stress will have been concentrated there and not the whole thing. It gets a little complicated. And I think that particular point is beyond the scope of the syllabus. But it is explainable, but you got to sit there and think about it for a really long time. And I haven't done that in a while, and I can't do that. So I'm going to go with beyond the scope of the syllabus, but hopefully done enough to convince you why. Yeah, it's complicated. It's a great question, though, and exactly the sort of thing that material scientists would tend to answer. And if I had any interest in doing that, I would still know how to do it. So, okay. Now, yeah, let's discuss something that's brittle. So brittle behavior is entirely different. So no, take two on that. So brittle behavior would look like it would go up to there, and then it would just go and snap. Just done. The end. Once you've hit your elastic limit, plastic behavior isn't really available. So if you try and extend it literally anymore, it just goes, nope, shatter, break, done. So that's brittle. And that's something obviously like glass. Let me see, in fact, if it's... And in fact, I'll tell you what, that is not universally true as well, because as I'm looking at the copper, no, it does still dip at the end. Like, yeah, if it's plastic, it does always have that kind of dip at the end. So this is for a wire. Not always, by the way, will it have this kind of dip into that kind of like lower bit there. So for instance, I can see in the book, they're giving the copper curve as being something that looks a bit more like straight line, straight line, straight line, straight line, and then it just sort of goes, and so this is copper. It doesn't have that kind of like dip and then going back up again. So every behavior, in other words, every material has unique stress strain behavior, which depends on like on an atomistic level what it's made up of, how easy it is for these atoms to slide past each other, all that kind of good stuff. Stress strain, elastic strain energy, we've talked about. Spring energy, we've talked about. Plastic behavior, elastic limit, then it goes plastic, you don't get the shape back. Brittle versus ductile, we've talked about. Good. Energy conservation, we've talked about the work done. Yes, there's one thing I want to say actually, which is sort of crossover. So I think it might even have been the last time I streamed on the physics side. No, last time was circular motion and simple harmonic motion, where we talked about damping. So one of the classic cases of critical damping was car suspension systems. So you're in your car, you drive into a pothole, you have springs that kind of absorb that, but you want critical damping. You don't want to keep oscillating forever. That would make the car ride very uncomfortable. So what happens is you have critical damping, you have these energy dissipators. What's going to happen is we can kind of combine this idea with the critical damping idea. Because we know it's a spring within its elastic limit. Oh, that's a good point, because that wouldn't be plastic flow. Hang on a minute. Let me have a quick look at this. So you have shock absorbers, which are springs, but the energy has to go somewhere. It has to go as thermal energy, but I suppose if it's a spring within its elastic limit, it would just load and then unload. So I was going to say something wrong. I was going to say that it might look something like this, where the energy in between, would be the energy stored in the spring and thus removed from the system in order to damp it. But that wouldn't be so, because that would permanently deform the spring every time you went over a speed bump, which clearly doesn't happen. This is a spring, so it's actually going to load and unload just in a normal straight line like this. In critical damping, you need something else to take that energy away. So I'm going to withdraw my statement about the sort of tie-in, but they do talk about, because this is springs and we are talking about sort of forces and extension, there is that tie-in you can make somewhat with the critical damping for car suspension systems. And we've spoken about Young's modulus, which is stress over strain. We've spoken about the graph. So I think we're okay, actually. So that seems to be everything in the material science bit. If you guys have any specific questions you've seen on this stuff, feel free to drop them in the chat, because I know there's some very interesting ideas here. Let me see if I can find anything interesting in the worked examples. Why don't I just, I'll go through one worked example, just because this has all been very abstract. Let's get some specific cases. So let's say June 2023 AQA, a moment's question involving Young's modulus. Common misunderstandings of energy. In fact, let me just go full comment section. Okay, I'll find the June 2023 next, but first, can you go over some common misunderstandings of energy? Yes. The thing about energy, whether it is in thermal energy or in mechanical energy, such as GPE, EPE, kinetic energy, the way to lay it out is to take it energy by energy. So what happens to the GPE? What happens to the kinetic? What happens to EPE? Do the individual equations, and then write to yourself, does it go up or does it go down? That way, when you're assembling the equation, you can say all the energies that go down equals all the energies that go up. So for instance, And this is also true for your further mechanics, by the way. So here, if we have, I've seen a specific equation, a sort of specific question where someone is going down a slope and then up a little hill. And so there's just a bunch of different stuff happening. There's like the GPE is going so in this case, the GPE is going down, but the kinetic energy is going up. But there's also work done against friction, which is going up. But there's also mechanical work done by the person, which has to be put into the system. And so there's a lot of different energies that can be accounted for. So one by one, like from like point A to point B, what is the change in GPE based on the question parameters? What is the change in kinetic energy? What is the work done against friction based on the question? And then then if that's not enough energy to account for the kinetic energy you have, then you have had to put energy in yourself by sort of pushing the ski poles. And so you can work that out. So do your individual energies and then think about how to assemble them in an equation. Yep. I'm just looking. Yeah, I think that's what I would say there. Now I'm going to quickly find this June 2023 AQA paper because apparently there's something combining moments and Young's modulus, which sounds very interesting. So AQA, A-level physics past papers. I'm going to find the 2023. It's going to be paper 1, AQA paper 1, 2023. I'm going to try and find this question. If you can drop in the chat, if you know exactly which question, that'd be great. But in the meantime, by the way, I hate particle physics. I hate it with the passion of 1,000 suns. I don't like knowing things. That's the problem. So I'm seeing, no, this looks like electricity. Then we're getting some optics stuff. Oh, here we go. Yeah, why don't I solve this? Okay, so I'll stop sharing screen. I'll bring the paper across. Let's start sharing the paper. Well, in fact, what I'll do is I'll do it properly. So I'll download it. Yeah. Okay. Right, let's go into this quickly. All right, so this is AQA 2023. You say it's question 5. Let's have a look. So I don't like the sort of physics live solves because I find them boring, but individual questions, then we can talk. So let's go through this question. You determine the Young's modulus of the material. Young's modulus is going to be the gradient. When you are finding the gradient of a straight line bit, make sure you find points that are as far apart as possible that go cleanly through the center of a square. So for instance, I know at some point it seems like it's tailing off. I don't know if it hasn't started tailing off by then, but this point here is one that I'm going to take. So for instance here, no, let me try that. I'm going to drop it down here. And I would say that the Young's modulus will be the change in y, which would be, now that's 150, 125, 120, 110, 105. So it's 105. Look at the units. Mega is times 10 to the 6. All over a strain, which is 7.5. Again, units times 10 to the minus 4. And this is important because the units for Young's modulus are very often gigapascals. So 105 times 10 to the 6 all over 7.5 times 10 to the minus 4. I'm not sharing full screen, so you can't see my calculator, but the answer is 1.4 times 10 to the 11 pascals, or 140 gigapascals, is the Young's modulus. Explain how this graph shows the metal is brittle, because you basically, you don't get this sort of ductile flow. You don't get very much extension past the elastic limit before it breaks. I would want to see. Now this is, oh, hello. 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 This is what you were on about. So here, the unloaded length of each steel wire is 1.2. We have the mass of AB, uniform beam, good. So that's in the middle. Suspended from a fixed horizontal support by two identical vertical steel wires. A lamp is attached to the midpoint. So in other words, because the beam is uniform and the lamp is attached at the midpoint, both of those weights act at the same point. So it would be 20.4 G acting at that point. Distance between the wires is 2 meters, which means each of these local distances will be 1 meter. We have the diameters of the wire and the Young's modulus. Calculate the extension of each wire. Okay. So what we know is that it should be equal in both because it's just like right down the middle. So I'm going to say the force. So we know that so the extension of each wire, we know the Young's modulus. So we know that Young's modulus is stress over strain. Let's work out the stress. So the stress is the force, which would be 10.2 G over the cross-sectional area, which is pi times r squared. Now the diameter is measured, not the radius. So it's 0.4 millimeters is the radius, and we square that. And if I run that, I'm going to go, oh, no, guys, I press buttons. I shouldn't press buttons. Yeah, so running this on my calculator, I get 10.2 times 9.81, which is the A-level physics value to use, all over pi times 0.4 times 10 to the minus 3, all squared. Whoop, press the wrong button. Is the force halved because it's for one wire? Yes. So I'm considering one wire, and it's only because they're identical wires and the force is exactly halfway in between. In theory, I could work out the moments from A and prove that the force in B is going to be half of this. But for 3 marks with a bunch of other stuff to do, I'm like, nah. So it looks like the stress is 199 megapascals. And we know the Young's modulus. So we can work out the strain would be 199 times 10 to the 6, all over the 2.10 times 10 to the 11. So in other words, it's the answer I just found divided by 2.1 times 10 to the 11. Oh, guys, I'm so bad at pressing the buttons. Really glad you're not seeing this. So the strain is 9.48 times 10 to the minus 4. And this is the extension over the original length. So the extension is that stress times the original unstretched length of 1.2. And then I get 1.14 times 10 to the minus 3 meters. In other words, 1.4 millimeters. So the right-hand steel wire is removed and replaced with an aluminum wire of diameter 1.6. So different diameter. So now we can't assume that the tensions are the same in both. The unloaded length of the aluminum wire is the same, so it's the same 1.2. When the lamp is at the midpoint, one of the wires extends more than the other. Oh, so that AB is not horizontal. To make AB horizontal, the lamp has to be moved to a distance x from A. Oh, that's very interesting. Okay, I'm really glad you brought me this question. So that's going to be x. So now we're going to have the mass of the lamp is 16. So 16G is acting at x. And well, let's also think about this. So The Young's modulus, that's 7 times 10 to the 10, so that's a lot less. Sigma equals E. So, okay, so let me just go through this. Okay. I'm just gonna do this generally. So we know we have that at X. We also know we have 4.4 G acting at a distance of 1 from both. The Young's modulus of aluminium is that. So we want the extension to be the same, but we don't know what the extension is. We do know what the sum of the forces is, though. And we know that if E is stress over strain, so I'm just writing down everything I know. That's force over area times L over extension, right? Okay. So that's in an individual wire. We know L, we know A for both, we know X is the same for both. So in other words, let's rearrange this for F. F is equal to A X E over L. And for all of the wires where this X is not that X, this is extension, we know the extension is the same in both wires. We know the area of both wires. We know the Young's modulus of both wires. We know L for both wires. We can work out the F, and their sum should be this. And then, okay, so I'm not seeing the strategy. This is a very good question. Thank you for this. Okay, so how would I do this? What do I know? This is one where I would probably need like a lot. Like I would 100% be getting extra paper for this. Young's modulus. I know. Okay, let's work this out separately. So the force on the aluminium would equal to the area, which is pi times 0.8 times 10 to the minus 3 squared, times the extension, which I'll call delta L, times the Young's modulus of the aluminium, which is 7.00 times 10 to the 10, all over the unstretched length of 1.2. So I can work that out as a expression of delta L. So pi times, and then I've got 0.8 times thingy squared times the Young's modulus of 7 times 10 to the 10, all over 1.2. So that would be sort of 100 and this amounts of delta L. And similarly, the force on the original wire, which was made of steel, would be equal to pi times the 0.4 times 10 to the minus 3 squared times its delta L all over 1.2. Oh, times of course, the Young's modulus of 2.1 times 10 to the 11. There's probably a better way of doing this, actually. I'm going to stick with this, and then I'll show you what I think the better way was. So if I plug this in now, that would have been 0.4 squared. And then this would have been 2.1 times 10 to the 11. I could have done this just sort of comparing it, because I'm seeing that the Young's modulus has a factor of 3 and the radius has a factor of 2. So there was probably just a much better way of doing that. 8, 7, 9, 5 lots of delta L. In fact, I will do that now. So yeah, this is time pressured in the real thing, man. So I know that A for the aluminum is 4 times A of the steel, because the radius is double. I know that the Young's modulus of aluminium is a third that of the steel. So you can also kind of compare the forces that way. So we can consider F of the aluminum all over F of the steel as being A of the steel, A of the aluminium times the extension, which is the same, times the Young's modulus of the aluminium, all over the length, which is the same. And you divide that by the A of the steel times the X, which is the same, times the Young's modulus of the steel times the length, which is the same. These cancel. So it would be and now the A, so that would be 4 times a third. So it's 4/3. That was a simpler way of doing that. So I shouldn't have done the thing on the left. That was how I could have simplified. Cool. Let me just, oh no. Utter disaster. Whoop. Come on. You can do it. Give me my space. Okay. So you get this ratio of 4/3. So the force here is 4/3 of that, which means that there's 7/3 in total. So if that is the force, that is 4/3 F, which means that 7/3 F equals 20.4 G. So the force here is 20.4 G. It's 3/7 of that. And I like the fact that it's over 7 because 9.8 is divisible by 7. So that should come to a nice clean number. So it's 3 times 20.4 times 9.81. All right, so that was really the trick. This was going to be really impossible unless you spotted... Oh, I thought that was going to be clean. Wait, what's 9.81 divided by 7? Oh, it's 9.8 divided by 7. Oops. So that force is 85.77 newtons, roughly speaking. And then let's take 4/3 of that. So times 4/3, which means this force, so that force there is the 85.77. This is 114.36-ish. And then we can do moments and say, God damn. And then say that 16G acting at a distance of X plus 4.4G acting at a distance of 1 equals 114.36 acting at a distance of 2. And so this thing times 2, and then we subtract 4.4G. So 16GX is equal to 185.55. Let's divide this thing by 16G. And we get that X is equal to 1.18 meters. That was insane. I have to check if I'm right. I am not at all confident on that. Thank you so much for bringing that. That was a fun question. Did I get that right? That was totally valid to get really stuck on that. First of all, did I get it correct? Let me check. 1.18. I did get it right. Extension is the same in each. So what were they saying? Hold on, let me stop share so I can show you the mark scheme. Woo, okay. Also, someone says in the comments, if you write outside the lines of the answer box, can you still get marks? No, you must keep within the lines of the answer box because the person marking your paper, hold on, let's have this conversation. The person marking your paper does not have the paper in front of them. They have had the paper scanned and they are doing it on their computer. What happens is you do not have one person marking your whole exam. Every single one of your questions gets sent to a different marker so that if you get stuck with a harsh marker, it kind of averages out, right? So it reduces that bias. You kind of reduce the average to the mean. So what it means is you actually do need to write within the box or else it's not going to scan properly. They won't see it on their screen. They can't give you credit for work they don't see. So very, very, very much stay within the lines. Now, if I bring the mark scheme over, I could have simplified that. So you could see me going through the thought process. It was not at all obvious what to do there. What I could have spotted, first of all, I got the ratios, which made my life a little easier. I spotted, well, that was 7. You can't see what I'm doing, so this is deeply unhelpful. Let me just share the entire screen. So I'm going to be flicking back and forth. So here, what did I spot? I spotted 2.1 times 10 to the 11 and 7 times 10 to the 10. I saw that as being a factor of 3. And I saw this as being double the diameter, which made me think to sort of link these to get that ratio between the forces. You could also have got that because the strain is the extension over the original length. That will be the same for both. So actually, because that's the same for both, that kind of cancels, and then you just get this. It's basically what I did. So you get the relationship between, yeah, basically that's what you got to do. So evidence of extension in being the same, good. Substitutes in, yes, you get 4/3 to relate the forces. And then you have to go through moments, and then you get 1.18. That was wild. So when I was just sort of doing the numbers, that was bananas. Simplifying the problem by making good use of ratio was how I was able to make a breakthrough into that problem. And then relating that the forces down have to equal the forces up. So you could work out the force in both wires and then use moments. But that was wild. Absolutely bananas. So thank you for that. Now, hopefully that makes sense about how to do the material stuff, but also look at that exam technique I did where I simplified by finding ratios rather than doing whole numbers. I think that is it. I think we have done paper 1. So what are we going to do next? So paper 1 is on Wednesday. Paper 2 isn't for a while. It is on Monday the 1st. We'll see how much time I have in half term, by the way, to stream, because that's going to... but I can definitely see... in fact, you guys can suggest to me what would be the most useful to help you guys with paper 2 and paper 3 stuff. I think paper 3 in particular, I'm going to want to do. If you guys also, I really like what you just did there. You guys have been doing all your past papers. You know the ugly questions. Just throw me the ugly questions for physics and I'll get those done. That sounds like a really good fun time. So we can kind of do this sort of general, and also like I've kind of covered, I think I've covered all of paper 2's material. Yeah, I have, which means that once we go past this, now that you've done paper 1, you can really have free reign on what we cover in these sort of like physics seminar streams. So feel free to drop suggestions either in the comments or in the Discord server. Obviously, feel free to be like, if you join live and drop something in the chat, I'm super responsive to that. So we can kind of treat it as like a sort of, you know, revision seminar where you kind of come and just ask me about random stuff. Be very happy to do that. Like very open to like helping you guys in the way that would be the most helpful for you. So we'll leave that there. I will see you guys for a live solve at some point next week, to be determined, on the paper 3 of the OCRB MEI series, which looks very interesting and doesn't seem to be particularly well catered for. So I'm really looking forward to that. Now, in the meantime, work hard. Ooh, can you go over paper 3 questions? Absolutely. Just generally difficult theory ones. Yeah, paper 3 is bad, and I don't like it. And I'm really glad I'm through to the other side of it. Sucks to be you. Sorry about it. So keep working hard. All the best of luck with your physics paper 1. I will see you on the other side. May the odds be ever in your favor. Take care. All right. See you guys next time. Bye-bye.